Hi, I am Neha Soni and my team members Amol Bodhare and Kaushal Ruparelia are presenting on finding longest repeating strings in genomes of organisms. Now let's see what is the main aim of finding longest repeating string in genomes of organisms. The main aim is to measure the similarity of genome sequences. Now let's see what is a sequence. A DNA of organism consists of like 4 types of nucleic acids: A, C, G and T, where A stands for adenine, C for cytosine, G for guanine and T for thymine. And the sequence of these 4 nucleic acids forms a unique sequence. The goal of comparing 2 strands of DNA is to determine how closely related 2 organisms are. Now, why using parallel processing for DNA sequencing? DNA sequences are large file and if computed sequentially would take over days to provide the output. While in parallel computation, the large sequences could be divided into number of small chunks or small blocks of sequences and computed on different machines. Thus, we use the cloud platform provided by Amazon, that is Amazon EC2 instance, to make cluster of 4 nodes and run the program parallelly. Now, before looking at the working of LCS, that is longest common subsequence, first let's be clear about what exactly is longest common subsequence. Now, usually if we think about longest common subsequence, what comes in our mind is pattern matching. But this is not the case. LCS is not same as pattern matching. In pattern matching, if you're searching for suppose the presence of string ABC or presence of sequence ABC, it should be the consecutive occurrence of ABC. There shouldn't be any character coming between A and B or B and C. But in LCS, the consecutive occurrence of ABC is not important. Only the occurrence in the same order is what matters. So if you're searching for A, B and C sequence in LCS, it might be possible that there's some characters present between A and B or present between B and C, but the order, that is A should come before B and C should come after B. Now let's see how do we calculate the longest common subsequence of 2 sequences given below, X and Y. So for calculating the common subsequence of length 1, what we do is we take one character at a time from X and we see its occurrence, at least one occurrence in the sequence Y. Similarly, for calculating the common subsequence of length 2, we take 2 characters from X, it could be AC, it could be CC or it could be CG, and we see one occurrence, at least one occurrence of the pair of characters in the sequence Y. Similarly, for calculating for common subsequence of length 3, we could take the subsequence ACC or we could take CCG and look for its occurrence in the sequence Y. The further explanation would be done by Amol.
Now, let's consider 2 long strings x and y, x with the size n and y with size m. The following algorithm explains how we can find the longest common subsequence. Since our x is shorter than y, so our algorithm is like this. For integer I from n to 1, find all subsequence of x with length I. Same for the we'll do it for y. Find all subsequence of y with length of I. If there is a common subsequence between x and y, then we have found our answer. This algorithm is quite simple and straightforward. We are aware of the fact that this algorithm will provide us with the longest common subsequence. The problem is how compact is this algorithm. Let us consider how many subsequence does x have with lengths of I. The answer is the following formula which is n factorial upon I factorial into n minus I factorial. The answer is the summation of this formula for every ith value. The complexity of this for loop is exponential in terms of n, which is denoted by big O of 2 to the power of n. Therefore, we were searching for a different approach. The next approach we came up with was dynamic programming. Dynamic programming was the best solution to tackle this problem in order to provide the most optimal or feasible solution. The following algorithm works down reversely to find the LCS with the highest ith value. This is done with the array Ci of j. The next thing is the drawbacks of using dynamic programming. We found out that dynamic programming provides the most optimal solution. However, this holds true only for a limited amount of data size. Executing LCS serially on a single system for the genome data turns out to be quite inefficient. We faced problems in terms of both memory and time. Therefore, the next step was implementing Hadoop to parallelly execute our problem. The further will be explained by Mr. Kaushal.
Hey, so I'm going to explain how the implementation of parallel programming has been. Now, why there's a need of parallel execution? So as Amol explained, we try to overcome the drawbacks of dynamic programming and also along with that try to improve the performance of the system. So now why is that so? We considered two samples for two bacteria, and in that we found out that every genome consisted of 4.5 million characters. Now that's approximately 60,000 lines of code, 60,000 lines, and each of the line containing 80 characters. So what we did in parallel execution is we tried to use Hadoop MapReduce as it was a text input and tried to divide the data into chunks and do a line by line comparison for sample A and sample B. So the 4.5 million character of data was divided into smaller chunks, and line 1 of sample A was compared with line 1 of sample B for the longest common subsequence. For output 1, what we tried to do is we tried to analyze the longest common subsequence line by line, and we tried to get the output as the length of the longest common subsequence. So for sample A and sample B, in line 1, if there are 40 out of 80 characters matching, so the output 1 of line 1 to line 60,000 would be in the range of 0 to 80. So for the output 2, that is to get the exact amount of or the exact length of the longest common subsequence, we took the output 1 as an input to the second phase and designed an output in such a way where we could calculate and merge our previous observations. For output 3, what we wanted to do is we wanted to find the longest common subsequence itself. So in order to do that, we again took the input files and tried to analyze them, and in one MapReduce, we were able to get the output. So that's all about Hadoop MapReduce. Now when we try to analyze the output from a serial execution compared to the parallel execution, we were of the opinion that the serial execution took roughly around 10 minutes for comparing the genomes of two bacteria. While on the other hand, the parallel execution took nearly 30 seconds and we were able to generate the output. So the output determines the strength of the longest common subsequence of the two genomes. Now the motivation for this is that we want to find the relationship between the two different organisms. And if we want to consider a real life application of this genome matching, it is nothing but DNA recognition. So with this, we would like to conclude. Thank you.